Hello everyone. Today we're going to learn how to do principal component analysis on R, okay? Or sometimes it's called factor analysis, but we'll do a principal components analysis on R. And in terms of the data, I'm going to use the Samsung data. And this is what this is that we asked respondents for the frequency of an application for tablets. So it was a survey basically asking the respondents, why do you use a tablet? And it was on a 0 to 10 scale, meaning that 0 you never use that application, and 10 you use that fairly frequently. And so there's 19 columns. So the data has, on the first column, it's the respondent's number, which we really don't need, but it's kind of just there. And all the other applications are whether you read a book or you're doing business or personal information management, education, entertainment, and so on and so forth, all the way down to weather. Okay, so now let's first read in the data. So this part is going to read in the data, and you will probably notice that it's a fairly standard read data file. There's your file subprovided by a tab. And like I said, we really don't need the first column, so I did a column class for this. Okay, if you don't like this part, you can definitely just use this part. Okay, and then in the results part, now you can probably just get the second from the 19th part. Okay, but however, I opted to use the call class. Okay, and I'm going to read in my data. So it seems that it's been read in. You can notice that on the console. And now let's run my principal component analysis. Okay, so I'm going to run it, and this seems to be the results. So it's fairly easy. Principal component analysis is done by using printcomp, and it gives me all these values that seems to be the principal components. Okay, so I get all these rotations and standard deviations for all these 18 principal components. Okay, so let's look at what are some of the attributes that we have in the results. Okay, so it seems that we have the standard deviation, rotation, center, scale, and the class is principal component. Okay, right now what we're really interested in is the rotations. So what I'm going to do is that I'm going to go into rotations and try to look at what the principal components are. Okay, so these are again the 18 principal components, and obviously we're probably not going to use all these 18 of them. We want to use some of the ones that are probably more important or probably more representing the data. Okay, so what I'm going to do is probably just get the first 5. Okay, I'm just going to get the first 5 here, and these are the first 5 principal components that I probably think that it's a better representation rather than using all 18 variables. Okay, so if I look at principal component 1, it has a high principal component number with V6, V11, 12, 13, I'm sorry, 14, and 16, and 19. Okay, so if I go back, what this is it's finance and navigation, and 12 was news, and it was reference, and sports and weather. Okay, so what people are using these applications for is that rather than saying, okay, these 6 are the top applications that are being used, but we can kind of sum that up and say that, okay, finance, navigation, news, reference, sports, and weather, this is probably more related to information principal component. Okay, so from the big data, we're trying to come up with a condensed or a more representative way to say this, and it seems that principal component 1 is finance, navigation, news, reference, sports, which is more about information related. Okay, Now let's look at the second one and try to see what the second one is trying to represent. Okay, let's look at the principal component numbers, and which has the higher number. It's V2, V5, and down. Here we go, V13 and V17. And if we check, it's going to be books, and then entertainment, V5 and then 13 is photo, and then it's going to be travel. Okay, so definitely different from principal component 1. It's probably more related to like fun or leisure, books, entertainment, photo, and travel. That's the component that is kind of representing. Okay, so that seems to be the second most applications that people are using from a tablet. Okay, now let's go to the third one here. And the third one, let's look at the ones that have the high values. It's going to be V3, V4, V7, and that's pretty much it, which is for right here, it's business, education, and medical and healthcare. Okay, it's probably more like a work related. If you're in a business, if you're in a education or in medical or healthcare type of industry, then it's probably a little bit more work related things. That is probably the third principal component. And now let's look at the fourth one here. Fourth one, it seems to have a high value with V8, 9, and 10. Okay, 8, 9, and 10 is fitness, lifestyle, and music. Okay, that definitely looks like more of a lifestyle or fun, a little bit different from leisure, but more of a lifestyle type of a principal component that you could probably attribute. And let's look at the last one, which is principal component 5. Okay, and principal component 5 has one big value, which is here we go, 15 and 18. Okay, which is 15 is social networking and utilities. So it's more about social or utility type of a seeker. It seems that that's the fifth most frequently used application. Okay, so from a big data set of 18 possible applications that you can probably use, you can probably sum up the big data into like more of a information component, or like a fun leisure component, work component, lifestyle component, and social component. So that's like the 5 main principal components that you can really condense the data set into, rather than trying to say that okay, all these 18s are the applications that people are using. Okay, so now, once we have that, you're going to probably decide, okay, I just used 5 of the principal components, but in mathematical terms, what are you going to use in terms of the number of principal components? Okay, in that case, what you really need to look at is what we call a eigenvalue. Okay, and if the eigenvalue is greater than 1, it means that it is explaining actually more of the data than it is not explaining more of the data. Okay, what does that mean? So adding another principal component, is that helping in terms of explaining the variances of that principal component? Okay, so if it's greater than 1, it is actually explaining more of the variance. If it's less than 1, there's actually more error term involved, so it's better off to leave that out. Okay, so I'm going to try to get the eigenvalue for all the principal components. Okay, and I just ran the eigenvalue, and let's see what the eigenvalues are. Okay, there we go. And not surprising, yes, the fifth one, 1, 2, 3, 4, 5, has eigenvalue that is greater than 1. Okay, and that's not a coincidence, because I almost arbitrarily chose 1 through 5 because I kind of knew the results. Yes, obviously before recording this video, I did look at the results, so I know which ones to choose. So yes, these 5 are the ones that you should choose as principal components and say these 5 are the data sets that I want to have. Okay. And now we talked about variances, and variances are the ones that you want to see in terms of how many percentage it is actually explained to the data. So if I run the variance data, and if I now variance, okay, I get that, and obviously the variance, if I add this up, this is going to be summed to 100, okay, which means that the first principal component, 29.3, it means that it is explaining 29% of data, okay? And the second principal component, it is roughly explaining 21%, and the third, it is 70%, and fourth, it's 13%, and the fifth one is explaining roughly around 6.3% of the variances, okay? So like I said, the more you have, obviously you are going to explain more of the variances, but there's actually a threshold that you want to say that, okay, after some number, then you're not going to really want to have that principal component to explain your data set. Okay. So now if I want to get a cumulative variances, just to kind of line up neatly and just make sure that everything sums up to 100, and if I do a cum var here, I'll cum sum to get the cumulative sum of the variances. Now you will probably notice that the last one is going to be 100%. Okay, and why do I use this? So we said we're going to use 5 principal components, and with those 5 principal components, what I'm trying to say is that actually with that, I'm explaining 86% of the data set. Okay, so just using 5 of the variables of the total of 18, I can still explain 86% of the variance, which isn't too bad. Okay. So now I'm going to just make this into a data frame just to make sure that I can get some graphs and things a little bit more neatly. Okay, so that is, I looked at my eigenvalue, variance, and cumulative variances for the first 5 of them. Okay, and it turns out to be like this. And again, eigenvalue, variance, and the cumulative variances. It seems that the system is kind of suggesting to use 6, but that's fine. You can use 6 or 5 is okay with me, but maybe they're trying to say that, okay, cumulative variances has to be greater than 90%, okay, but that's not a big deal, okay. So in that case, let's try to draw a bar chart with those 6 variables. Okay, what I'm going to do is that I'm going to use a var chart, and I'm going to use the first column. Okay, first column, if you notice that that's going to be the eigenvalue. Okay, if I run this, now there we go. I didn't get anything here. Well, is there something wrong? Okay. Figure margins are too long. Okay. Okay, there we go. Okay, so yes, you can notice that the first principal component is roughly around 5.27, and the second one was 3.7, and so on, and all the way down to the 6th one. Okay, and in terms of the second variable, which is going to be variance, I'm going to use the second variable for running that, and if I were to run this, and you would notice that this is now the scale has changed from 0 to 25, and this is just the principal components from 1 to 6, and how you would notice that it actually decreases from the first to the last. Okay. So that was a very simple way of running principal component analysis on R, but some of you will probably ask, okay, now you have principal comp, print comp, but we actually used, in our case, it was prcomp, okay? So yes, R provides 2 functions, prcomp and printcomp. A lot of people ask, okay, what's the difference? Actually, it's pretty much the same result. It does use a little bit different computational methods. Okay, but in reality, you're not going to see a whole lot of difference. Okay, so that is, let's try to see what type of result that I'm going to get. Okay, so now here I probably need to change this back to not using the second one and from the 19th. Okay, so now this is the standard deviation, variance, and the principal component cumulative proportions. And if you remember, it was 29.3, 20.6, and so on. And yes, that was pretty much the same value that I get, 29.3, 20.63, and so on. So yes, you will probably not notice a big scale difference whether you're using a print comp or PR comp. And if you really want to get into all these details of how they are going to be calculated, you could obviously refer to the help page. And you can go down. What PR comp uses here is that, okay, calculation is done by singular value of decomposition of the data matrix, not the eigenvalue of the covariance matrix. Okay, whereas if you use PR comp, I believe it is using the eigenvalues. Okay, so here we go. Calculation is done by using the eigenvalue of the correlation covariance matrix. Okay, so that's the computational differences, but in reality, you're not going to get a whole lot of differences in terms of the two methods. Okay. So that's how to run principal component analysis using R. We both used prcomp and printcomp for giving those examples. Okay. Hope you enjoy the video, and I'll probably see you on the next video. Okay. Thanks. Bye.